Cylindrical coordinates. Cylindrical coordinates is just changing x and y into polar coordinates. So we know that we can change x for r cosine of theta and y for r sine of theta using the polar coordinates formulas. And the c will leave it the same. So now instead of expressing the point or representing the point by the three numbers x, y, and z, we represent the point by r, theta, and c. So this is the new representation in cylindrical coordinates. The idea of cylindrical coordinates is more or less the same idea as polar coordinates. We are going to be able to express certain integrals easier in cylindrical coordinates. For that, we will have to first compute the volume of cylindrical boxes. And if you remember, it's not a big deal because it's going to be the area of the base times the height. The area of the base is just the volume of a polar rectangle, and the height is just delta c. So notice, and remember that r star is just the average radius. So in order to change to cylindrical coordinates in a triple integral, the only thing that we have to do, well, if you remember, we can define the triple integral in cylindrical coordinates as this, using Riemann sums, and that's going to give us the formula. So the formula is going to be just given by this. You have to change x and y into r cosine of theta, r sine of theta, changing everything in polar coordinates, and then just adding an extra r as in polar coordinates. This is every time that you're trying to integrate over a cylindrical box. In other words, r moves from a number to a number, theta moves from a number to a number, and c moves from a number to a number. Now we're going to see how to evaluate triple integrals in cylindrical coordinates. Now, if you have simple regions, in other words, if you have the c moves between two functions that depend on y, and we have that the region D happens to be a region that you can express as a simple region in polar coordinates, the thing that you end up is that you can take this integral but change into cylindrical coordinates at the end. The things you can have is this formula that we have right here. So you would change this function such that it depends on r and theta, and those are the limits of integration that we put over here. Remember, x and y, we change them into polar coordinates. We are the extra r, and then we go, we have the extra r, and then we go, the c moves between two functions that depend on r and theta, then we integrate with respect to r. R could move between two functions that depend only on theta, and theta moves between numbers. So start putting the functions inside with more variables inside, and then you go working your way backwards until you have the limits, the variable that moves between numbers at the end. So let me give you an example. Let me try to find the volume of the solid enclosed by this cylinder and this parabola. So first of all, the cylinder looks like this. The paraboloid looks like this, and the volume that we're trying to find is this, the volume of this solid B. So first of all, in cylindrical coordinates, a cylinder has equation r equals 2. Remember, we have to change everything in cylindrical coordinates. So r equals 2 because r squared equals to 4, so r is equal to 2. The paraboloid is represented by c equal to r squared, and the xy plane is described by c equal to 0. So notice that now everything that has either r's, thetas, and c's. Once we have that, then we take the cylindrical coordinates, and then we express that in cylindrical coordinates. The first thing that I want you to notice is this is the way the variables are going to, the bounds of the variables. And let me just tell you why. Theta goes from 0 to 2 pi because you are moving all the way around. R goes from 0 to 2 because you are taking everything that is between the c-axis and the cylinder that has radius 2. And c moves between 0 and r squared, and that's just because the c is going to stop once you get to, once you have this particular set representation of the solid, then setting up the integral is pretty easy. Just take the double integral dv, and then we integrate first with respect to c, so c goes from 0 to r squared. then we can integrate with respect to r or with respect to theta, doesn't matter what. Let's say we integrate first with respect to r, so we go from 0 to 2, and then we integrate with respect to theta, and theta will go from 0 to 2y. Notice that here we have this extra r, and this extra r is given by the change of variables from x, y, and z to r theta z. So now we just do the evaluation. I'm not going to talk a lot about this, but at the end we end up that the answer is 8pi. Now the thing that I mean, you can verify it and you can pause and do it yourselves. Remember, you can always do that. The thing that I want you to make you notice is that we can use the previous integral doing something that we did before, that is triple integrals of the xy regions, more or less the thing that we were saying. First integrate with respect to c, and then worry about the other integral. And the other integral, notice that it's a polar integral, and that's why you have this setup. So cylindrical coordinates can be done with things that we have done before, because cylindrical coordinates consist on changing x, y to polar coordinates. So basically you are doing a double polar integral. The only difference is in cylindrical coordinates you are actually setting up the integral all at once.